Statistics plays a significant role across the physical and social sciences, and it's arguably the most salient point of intersection between diverse disciplines.
Statistics is the common language of science. Scientists use statistics to convert data into useful information. This is exactly what you will do in this course. Through your own original research, you will convert existing data into useful information. You'll use data to tell a story that's of interest to you and of value to others. Statistics is therefore a process where we are collecting data, summarizing data, and interpreting data.
The process of statistics starts when we identify what group we want to study or learn something about. We call this group the population. The word population, and throughout its entire course, is not just used to refer to people. It is used in a more broad statistical sense, where population refers to an entire group you want to focus upon. This can be an entire group of people, or animals, or insects, or inanimate objects like apartment buildings or craters on Mars.
For example, we might be interested in the opinions of the population of U.S. adults about the death penalty, how the population of mice react to a certain chemical, the average price of the population of all one-bedroom apartments in a certain city. Population, then, is the entire group that's the target of our interest. In most cases, the population is so large that as much as we want to, there's absolutely no way that we can study all of it. A more practical approach would be to examine and collect data only from a subgroup of the population, which we call a sample. We call this first step, which involves choosing a sample and collecting data from it, producing data. Since, for practical reasons, we need to compromise and examine only a subgroup of the population rather than the whole population, we should make an effort to choose a sample in such a way that it will represent the population as well. James Thompson has been studying pollination success of an obscure flower that blooms at high altitudes, the glacier lily.
We're looking at a high-altitude species, and as people interested in global change and climates have realized, this is where we might first see things like species doing poorly because the situations have changed. And in fact, there's a lot of focus on high elevation research in the general context of climate change.
There are millions of these flowers across the Rockies, and Professor Thompson cannot study them all. He has to choose a sample.
If I'm to say anything accurate, those data have to really reflect what's happening out here. So for instance, when I look at a sample of flowers, I have to be thinking all the time about whether I'm selecting a set of flowers that's adequately representative of the whole of what I want to talk about.
This is true whether we're studying flowers, craters on Mars, or the opinions of U.S. adults regarding the death penalty. Our sample would not represent U.S. adults if we only asked Republicans or only asked Democrats. Such a sample would not represent the population. Data sets can be very different depending on what is being studied. This data can take the form of answers to survey questions, tables of numbers, such as crater details, or in the case of glacier lilies, observations collected over many years.
Essentially, I've asked a very simple question: what causes a flower to be a success? Does it get pollinated? Does it set a fruit? Does it make seeds? How many seeds does it make?
To make sense of this data, it needs to be summarized in a meaningful way. This is called exploratory data analysis. Exploratory data analysis often reveals new ways to think about the data.
As frequently happens in science, the more carefully I looked, the more things I saw to interest me.
Exploratory data analysis helps scientists refine their questions and sometimes even reveal entirely new questions.
If climates are changing, relationships between plants and pollinators and other mutually beneficial relationships, those may be disrupted.
Scientists studying climate change have often wondered what effect a warming climate will have on the relationship between plants and animals. Is it possible that small changes in climate could have a big impact on these relationships? Exploratory data analysis suggested that is a question Professor Thompson might be able to answer using 30 years of data. This leads up to the final step, inference. What can we infer about the population as a whole from the data in our sample? Remember, after exploratory data analysis, we're able to ask specific questions of our data. Inference is where we come full circle with the hope of revealing new knowledge about the population. So what can Professor Thompson infer about glacier lilies? What his data reveal is that glacier lilies and the bees that pollinate them are becoming separated in time. As the climate warms, lilies bloom sooner, before the bees arrive.
My paper on the glacier lilies, as far as I can tell, is the first demonstration of it, or the first even plausible demonstration of it. It's not an easy thing to show. It's an easy thing to say, hey, this could happen. My long-term data sets have allowed me to do is to say, yeah, and it looks like it has happened.
James Thompson was able to explore his data to show how climate change causes plants and animals to become disconnected in time. You too will be looking at large data sets and asking new questions of interest to you. You won't be creating new data, but you will create new knowledge through exploratory data analysis and inferential data analysis.
Statistics education is most often conducted within a discipline-specific context or as generic mathematical training. Our goal is instead to create meaningful dialogue across disciplines. Ultimately, this experience will help you on your way to engaging in interdisciplinary scholarship at the highest levels.
But what do we really mean by data? Put simply, data are pieces of information about individuals organized into variables. By individual, we mean a unit of observation. An observation, or unit of observation, refers to a particular person or a particular object, any particular unit of observation within your study sample. By a variable, we mean a particular characteristic of the unit of observation. At the person level, we might collect data on height, weight, gender, race, etc. If we're collecting data on a sample of cars, we might measure variables such as color, tire size, mileage, model, number of seats, etc. If our sample includes cities, we might measure variables such as population size, tax revenue, energy consumption, number of hospitals, and so on. A data set is literally a set of data that's made up of individual observations and variables. Data sets are typically displayed in tables, in which rows represent individuals or units of observation, and columns represent variables. Here is a data set that shows medical records from a survey. In this example, the units of observation are patients, and the variables are gender, age, height, weight, smoking, and race. Each row then gives us all the information about a particular observation, in this case, a patient, and each column gives us information about a particular characteristic of all the patients.
Variables can also be classified into one of two types, quantitative or categorical. Quantitative variables take numerical values and represent some kind of measurement. Categorical variables, on the other hand, take category or label values and place an observation or individual into one of several groups. In this example, there are several variables of each type. Age, weight, and height are quantitative variables. Race, gender, and smoking are categorical variables.
Notice that the values of the categorical variable smoking have been coded as 0 or 1. It's quite common to code the values of a categorical variable as numbers, but you should always remember that these are only codes, often referred to as dummy codes because they have no arithmetic meaning. That is, it doesn't make sense to add them, subtract them, multiply or divide them, or even compare the magnitude of these values. Finally, a unique identifier is a variable that is meant to distinctively define each of the units of observation of your data set. Examples might include serial numbers for data on a particular product, social security numbers for data on an individual person, or maybe random numbers generated for any type of observation. To help us organize our data, every data set should have a variable that uniquely identifies the observations. This variable is particularly useful if you ever need to merge information across different data sets. In our example, the patient number 1 through 75 is the unique identifier.
Relying on data sets, statistics pulls all of the behavioral, physical, and social sciences together. It's arguably the one language that we all have in common. While you may think that data is very, very different from discipline to discipline, it really isn't. What you measure is different, and your research question is obviously dramatically different. Whom you observe and whom you collect data from, or what you collect data from, can be very different. But once you have the data, approaches to analyzing it statistically are often quite similar across many different disciplines.
Since we will not actually be producing data in this course, your first step will be to choose a data set that offers the opportunity to conduct research on a topic of interest to you.
A few of the data sets that are available include the National Longitudinal Study of Adolescent Health, commonly known as AdHealth. This is a nationally representative school-based survey. Wave 1 of the survey included adolescents in grades 7 through 12 in the United States. AdHealth includes surveyed data on social, economic, psychological, and physical well-being of adolescents. Next is the Mars Crater Study. As you may know, the planet Mars has terrain that is heavily cratered. These craters were created about 4 billion years ago during a period of heavy bombardment from asteroids, protoplanets, and comets. Made available by researchers at the University of Colorado Boulder, this data set includes characteristics of more than 350,000 of these Mars craters. Also available is a portion of the Wave 1 National Epidemiologic Study of Alcohol and Related Conditions, commonly known as NESARC. This is a representative sample of the U.S. adult population age 18 and older, and it includes data on mental health and substance use disorders that are experienced by adults. Another data set is the Gapminder data set, which is made available by gapminder.org. It includes numerous measures from 195 countries. The data have been collected from various sources, including the World Health Organization, the International Agency for Research on Cancer, the United Nations, and the World Bank. In order to help you learn more about these data sets and which one you are most interested in, you'll be reviewing the available codebooks from these data sets. Sometimes called data dictionaries, codebooks commonly offer complete information regarding a data set. That is, general topics addressed, questions and/or measurements used to record each of the variables, and in some cases, the frequency of responses or values of each of the variables. Reviewing a codebook is always the first step in research based on existing data. First of all, codebooks can be used to generate research questions. Second of all, data is often useless and completely uninterpretable without them. The codebook describes how the data are arranged in the computer file, what the various numbers and letters mean, and any special instructions on how to use the data properly. Like any other book, some codebooks are better than others. In the AdHealth codebook, each variable has a description of what is measured. In this case, it's the question of what grade you're in. A codebook will also include the various measurement or response options. For this variable, possible response options include 7th through 12th grade, refusal to answer the question, a legitimate skip for those not in school, don't know, and the school does not have the grade levels or the question is not applicable. Aside from including a listing or description of the response options for the variable, the codebook will also include corresponding values that can be found in the dataset. As we saw previously with the medical records dataset example, datasets typically include numbers rather than words. So for categorical variables, such as grade level, each of the response options has a corresponding numeric value, and it's that numeric value that can be found in the dataset. You can see that 7th through 12th graders are logically coded as the number 7 through 12. 96 indicates that the adolescent refused to answer. 97 indicates a legitimate skip for the adolescents who are not currently in school. 98 indicates don't know, and 99 is recorded in a case where the school does not have grade levels. These numeric values are known as dummy codes, as they are included in the dataset, but they carry no direct numeric meaning. Here's an excerpt from the Mars Crater Codebook. It includes a description of the variables for the crater's name, latitude, longitude, and diameter. Also the depth of the crater's rim, as well as the variable's name in the dataset. Because most of these are quantitative variables, rather than listing a response option, the codebook includes a description of how the variable is measured. For example, latitude is measured in decimal degrees north, longitude is measured in decimal degrees east, and both diameter and depth are measured in kilometers. From the Gapminder dataset, we see a slightly different look to the codebook, but very similar features. You can see that the middle column describes each of the variables. The column on the left indicates the variable name used in the dataset, and finally the right-hand column lists the source of data. Again, these are quantitative variables. The codebook includes information about how each of these variables were measured. You can see that income per person is measured in US dollars, alcohol consumption is measured in liters of pure alcohol, armed forces is measured as the percent of the total labor force, and breast cancer rate is measured as new cases per 100,000 females.
So I chose Ad Health. I was really interested in health and specifically for young adults or adolescents.
Me being natural sciences, I was kind of drawn to the Mars crater study.
I knew that I wanted to connect it to whatever I'm doing with music and Latin American research.
So I use the Gapminder dataset. It's more worldly, economically excellent for comparing things across countries.
My data came from Ad Health.
I think it was about 39 different code books, and each of them could have up to like 30 different questions. So we had a lot of data that we could look through. But it was organized into topics, so I looked at the code book that discussed parental relationships. I looked at the code book that discussed sibling relationships.
They were describing these craters with like such funny descriptions that I would never have thought of. And so that kind of drew me in. Like I was wondering why scientists were naming these things.
Each student can look at the same data set but come up with a different research question, and they can choose to analyze it in a different way. And where they take that is completely their own.
Now you have a general feel for datasets, variable types, and codebooks. The next step is to select one of the datasets: Ad Health, Mars Craters, NESARC, Gapminder, or another one that you've chosen out of the datasets that have been made available to you for the course. Select a dataset that includes variables in an area that interests you.
Once you have selected a dataset, identify a specific topic of interest and print those pages of the codebook that include the variable or variables that measure your selected topic. Note that many codebooks, including those of NESARC and Ad Health, are too large to print. So it is very important to create your own personal codebook with only those pages that include the variables that you would like to examine.
Our example comes from the NESARC dataset and our chosen topic is nicotine dependence. There are several variables related to nicotine dependence, and we can see two here: lifetime nicotine dependence and nicotine dependence in the past 12 months. A value of 0 for each of these variables indicates no nicotine dependence, and a value of 1 indicates the presence of nicotine dependence. The name of these variables are tab12mdx and tablifedx. We'll use these variable names when we begin to work with the data.
We're not suggesting that this topic is more or less interesting or more or less important than any other. What's important is that you pick a topic that is of interest to you. We've chosen to look at nicotine dependence.
Once you have a topic and have printed the codebook pages that measure that topic, it's time to build a research question. One of the simplest research questions that can be asked is whether two topics are associated with one another. For example, is medical treatment seeking associated with income? Is crater depth associated with crater diameter? Is water fluorination associated with number of cavities during dentist visits? These data sets are vast, so there are many potential associations to explore. Let's look at our chosen example, nicotine dependence.
First, I need to determine what it is about nicotine dependence that interests me. It strikes me that friends and acquaintances that I've known throughout the years that became hooked on cigarettes did so across very different periods of time. Some seem to be dependent on smoking heavily soon after their first experience with a cigarette, and others after many years of generally irregular smoking behavior.
We decide that we are most interested in exploring the association between smoking behavior and a nicotine dependence. We believe that they are positively associated. That is to say, the more an individual smokes, the more likely they are to be nicotine dependent. We're also wondering how much a person needs to smoke in order to be nicotine dependent.
We continue to read through the NESARC codebook and find that smoking behavior has also been measured in this sample. So next, I take a step similar to one that I just took when choosing nicotine dependence. That is, I identify the variables that measure this second topic, smoking behavior, in my data set. The variables I choose include cigarette smoking status, usual frequency, and usual quantity.
During your second review of the codebook for the dataset that you have selected, you should also identify a second topic that you'd like to explore in terms of its association with your original topic. And again, print those pages of the codebook that include the variable or variables that measure this second selected topic.
The research question finding was kind of hard for me, but I found it, and it was a lot of trial and error and a lot of searching for all these different code books.
I chose to do a project to look at the association between adolescent self-esteem and the level of parental involvement, and to see if there is a correlation there.
So for my project, I looked specifically at intermediate craters, layered ejecta morphology, which is basically like if you were to stomp on a pedal or like step on a pedal, like you would create a splash that would just like come out like this. And then so that is what we call like an ejecta.
So the question that I got invested in was the relationship between parenting or parental styles and further adult relationships.
I looked at binge drinking young adults and treatment-seeking patterns based on arrests.
Some questions almost have never been really asked, at least not in a statistical manner.
We're encouraged to do original research, so actually we're not even supposed to do what other people have done. We're supposed to look at information that we're interested in, find out, where research has stopped, and ask the next question.